Hello everyone, welcome to Headway Civil online study. In today's video, we'll be learning about the soil improvement technique by the process of compaction. So what is compaction? It is the process by which soil particles are artificially rearranged and packed by some mechanical means to increase the unit weight of the soil by the expulsion of air from the voids. So what we are trying to do by this process is we are trying to rearrange the soil particles by some mechanical processes, and by increasing its dry density we are expelling the air from the voids. So compaction of a soil is generally measured in terms of the dry unit weight of soil. As we already know that the dry unit weight of soil can be expressed as gamma D equals to gamma divided by 1 plus W. What is gamma? Gamma is the bulk unit weight of the soil, or we can say it is the total unit weight of the soil, and W here it is the moisture contained. There is another equation of gamma D that we know is equals to G into gamma W divided by 1 plus E. These two equations will require while finding out the compaction curve and doing the problems on compaction. So let us move on to the factors that affect compaction. There are two factors. The first is the moisture content that we already know is W, and the second is the compactive effort. Compactive effort is the amount of energy that is imparted to the soil. While studying the process that we follow while doing the compaction, this portion of compactive effort will become clear to you. Next, let us look at what are the lab methods that we follow while doing the process of compaction. The first is the standard Proctor test, and the second is here it's given is the modified Proctor test. Both the Proctor tests are done in order to find out the dry density of the soil. So what we do is we take a certain quantity of air dried soil and we mix it with some amount of water. So if we consider, say we take m1 gram of say soil and we mix it with say W1 water content, or we can say the moisture content of water, we mix this soil with thoroughly. Then what we do is we take a cylindrical mold and we say this is the mold that we are taking, this is a cylindrical mold, and we fill it up in 3 layers in case of standard Proctor test and in 5 layers in case of modified Proctor test. 3 layers means what? See, you can see over here the layers are well defined here. This is one layer, this is second, and this is third. So total layer that we use is 3, and here it's so it's 1, 2, 3, 4 and 5. So total layers we take here is 5. The soil mass is placed in 3 layers, and with each layer is subjected to 25 blows of hammer. This is the hammer that we take. This is the hammer that we take. In case of standard Proctor test, its weight is 2.5 kg. In case of modified Proctor test, the weight of hammer we consider is 4.5 kg. Okay, this hammer is taken up to a height of 304.8 mm and is subjected to free fall. That means we are lifting it up to certain height, and again we are free falling it. We are releasing it from this height. Okay, this way for each layer we tamp it with 25 blows. The blows here and in this case, both the cases, the number of blows is 25 for per layer. After compacting it with this, we change the second portion. What we do is we find out the dry density of the soil. As I already said that dry density is gamma by 1 plus W, and for this cell what will be the gamma value? Gamma will be the weight of the soil that is taken divided by the volume of the soil. So here the volume of the mold, if we can know this cylindrical mold, if you know its volume, that will be the volume of the soil itself. So if we divide by the weight of the soil, we'll get this gamma value, and gamma will be a constant value for a particular process. Okay, next what we do, in first case we took water content as W1. Say in second case we change this water content as W2. Next we'll take W3, W4, and for every portion we'll find out this gamma D value. Say is gamma D2, gamma D3, gamma D4, and for the first one let it be gamma D1. What we'll do now is we'll find out the gamma D value for each of the portions. Once we get this dry density value, we will plot a curve between the dry density, or we can say the dry unit weight of the soil, and the moisture content. So here in this case, the modified Proctor test, as you can see, the compaction is done in 5 layers, and each layer is subjected to 25 blows. The weight of the hammer is 4.5 kg, and the height of free fall in this case is considered as 457.2 mm. So what we mean by the compaction energy? Here you will see I wrote it in a tabulated form. Say for the first one, that is the standard Proctor test, as you can see over here, the weight of the hammer is 2.5 kg, height of drop, here it was 304.8 mm. I just approximated the value as 310 mm. Here as you can see it's 304.8 mm. So I've approximated it as 310 mm. The number of layers that we follow here is 3, and number of blows each layer is subjected, that is per layer is 25 blows. This, if you can multiply this all together, that means 2.5 into this, and into this, this comes out to be somehow the values. You just check the this unit wise. And in modified Proctor test, I already told the weight of the hammer is 4.5. The height of free fall, here it was, you can see over here, the accurate one is 457.2 mm, but I just approximated the value as 450 mm. You remember this value itself because that is difficult to be remembered. The number of layers is 5, and each layer is subjected to 25 blows. So this will come out to be a compaction energy of 2700. For example, if you forget the compaction energy somehow, what you will do is, for you just multiply this 4.5 into 450 into 5 into 25. The amount that will give, this will give you your compaction energy. Okay, the same goes for the standard Proctor test. This is for the modified Proctor test, as you can see. So what we need is the weight of the hammer, the height of the free fall of the hammer, the number of layers, and the blows per layer. Okay, so question often comes as, find out the ratio of the compaction energy between the standard Proctor test, modified Proctor test, or we can be asked as modified Proctor test and standard Proctor test. So what we do is, we can, if you remember this value, it's well and good. If you don't remember, try to remember these values like weight of the hammer, height of drop, layers and blows. You should remember these values. So if we divide this 2700 divided by 600, this will come out to be somehow like 4.5. So remember, the ratio of the compaction energy will come out to be 4.5 if we divide this modified Proctor's compaction energy with the standard Proctor's compaction energy. Next, moving on to the moisture density curve, or which we know as the compaction curve. So the values that we have obtained, say gamma D1, gamma D2, gamma D3, corresponding to the moisture content we have taken as W1, W2, W3, we plot a curve, and the curve shows somehow a curvilinear pattern. This here, there are two curves that has been shown. The first one, as you can see here, is for the standard Proctor test curve, and the second curve, the top one, is for the modified Proctor test. So we can see one difference between these two curves, that see, the modified Proctor test curve is somehow shifted more towards the left side, because in terms of here, in here we saw the compaction energy in case of modified Proctor test is more as compared to the standard Proctor test. So what happens is, we can achieve a greater dry density in case of modified Proctor test at a smaller moisture content term, or we can say at a smaller moisture content. For example, here we are at this is the dry density since it's attaining its peak over here. So it's a peak that is being attained over here. So if you just draw a straight line from here, somehow the moisture content, say it will be 14, say somehow at 14 percent of moisture content we are attaining a dry density as maximum over here, whereas here we can attain a dry density like this is the optimum moisture content, this is the maximum point of here. Here we can see if you plot this up, or we can say this is somehow coming out to be 16, or we can say maybe 15. So it's at 16% we are attaining the dry density as maximum in case of standard Proctor test, whereas we are attaining a maximum dry density at 14%. So at smaller moisture content, a greater dry density, or we can say the dry unit weight, can be achieved in case of the process where the compaction energy is greater. Now, why the pattern of the curve is somehow like this, why it's increasing, attaining a peak, and then again it is decreasing. So at low moisture content, the internal friction and adhesion between the particles is contributing to resist the compaction. As we are increasing the water content, the particles develops film of water around their particles, and which helps in lubricating those particles to slide one above the other, thereby increasing its dry density. And after once reaches this peak value, as you can see over here, it's reaching its peak value, this point, or we can say this point, again it is showing a decreasing pattern. This decrease is due to water starts replacing the soil particles as it becomes more than this value. Say this is 15 or 16, if it's greater than this, maybe 17, there will be a decrease in this dry density portion. Right, so the value of moisture content at which the maximum dry density of the soil is attained for a given compactive effort is termed as optimum moisture content. For this curve, for the standard Proctor test curve, so for this test, for the standard Proctor test curve, the maximum, this will be my OMC value, that is my optimum moisture content, and for this the modified Proctor test curve, my moisture content that we will attain is 14%. So the corresponding value of water content for which we are getting the maximum dry density, or we can say the peak value of dry density or dry unit weight, is termed as optimum moisture content. Now let us move on to the next portion, that is the zero-year void line. So what is a zero-year void line? It is a plot between the dry density and water content corresponding to S equals to 100%. So what is S? S is the degree of saturation. That means it's the volumetric ratio between the water and the number of and the amount of voids that is present. So S we know is equals to volume of voids. When we are considering it as 100%, that we are considering it as, since soil is a three-phase system comprising of say air, water and solids, that means there is no air that is present. Air is 0. That means the volume of voids is totally filled up with volume of water. In theoretically this is possible, practically it can never be achieved. Now in case of zero-year void line, how to find out its dry density? We know the equation as gamma D equals to G into gamma W divided by 1 plus E. Again, another equation that we know is GW is equals to AC. So since zero-year void line corresponds to S as 100%, or we can say is as 1, so we can write E as equals to GW. So if you substitute this value of E as GW in this portion, what we get is gamma D as G into gamma W divided by 1 plus GW. So this is the equation that we get for finding out the dry density corresponding to the zero-year void line. In the graph, you can represent the zero-year void line as this. As you can see over here, For the 100% saturation line is the 0-year void line, which has been shown by a straight line. This is bolded straight line that has been shown over here. I hope you people are getting this. This is the bold straight line, as you can see, it is being shown over here. Okay, this will be completely, somehow it will be in a decreasing manner, and it will be parallel to the right side of this curve after it's achieved the moisture content. We can find out for other degrees of saturation like 90% or 95% also. You can find the gamma D value and corresponding to its moisture content. Now let us look at to the effect of compaction on engineering behavior. So compaction increases the dry density of the soil, as you have already seen through the graph. In turn, so once the dry density is increasing, or we can say the years are getting expelled from the voids, what is happening is the shear strength and the bearing capacity is increasing. It reduces the permeability of the soil, and in turn the settlement will also reduce. There are a few of the characteristics of the soil which we need to remember corresponding to the dry side and the wet side of optimum. So which is considered the dry side and our wet side? For example, if we draw a curve somehow like this, I'll show over here itself. Say the plotting was between the unit weight, dry unit weight, and the moisture content, as we have seen earlier. Say for example, if you get a curve somehow like this, right, and the peak value that we achieve corresponding to the water content, the maximum dry density we achieve is at optimum moisture content. The left side of it is considered as the dry of this optimum, and the right side of the OMC is considered as the wet side of optimum. Okay. So what are the characteristics on the dry side and the characteristics that on the wet side? On the dry side, we find the structure as flocculated. What do you mean by flocculated structures? The structure will somehow have edge to edge, or we can say edge to face orientation, somehow like this, edge to edge, or we can say edge to face orientation, somehow like this. And on the wet side, the orientation is dispersed. Dispersed structures somehow have parallel orientation, that means they will have face to face orientation, somehow like this. So this will be flocculated, this is dispersed. The questions generally come from this portion. The dry side of optimum represent what structure, the wet side represent what structures. These are the question. Remember, the dry side, the shear strength will be more, and in the wet side it will be less. Compressibility will be less on the dry side, more on the wet side. Permeability will be more on the wet side, less on the dry side. Swelling more on the dry side, and it's less on the wet side. And shrinkage is less and more on the wet side. So just try to remember this characteristic. Out of this all, this permeability and swelling, these things you will definitely remember. The most important thing you need to keep in mind is the structure. The flocculated will be on the dry side and dispersed will be on the wet side. This question is quite common. Next, moving on to the selection of equipment for the compaction in the field. So depending upon the type of soil, we select the compacting equipment. So for the first one, that is for the cohesive soil, the type of compacting equipment that is selected is shift foot roller or rubber tired rollers. And for cohesionless soil, the type of instrument selected is, or we can say the equipment is, rubber tired roller or vibratory roller. So this diagram that you are seeing over here, the first one, it represents it's a shift foot roller and is most common for the cohesive soil. Okay, the second is the rubber tired rollers, which is done for both cohesive as well as cohesionless soil. And the third one that you can see over here is a vibratory roller, which you generally seen on roads compaction while making roads and all that. You'll find this equipment very common. Okay, so if the question comes the most suitable equipment for compacting cohesionless soil, you will answer it as vibratory roller, because this is the most suitable one out of all, is the vibratory roller. And the most suitable one for cohesive soil is the sheep foot roller. These two questions are very common. Next portion that we'll see is the relative compaction. So relative compaction is the ratio between the field dry density and the maximum dry density in the lab test. And relative compaction, remember, it's always expressed as percentage. Usually 90 to 97% of relative compaction can be obtained, and we are able to obtain this portion as this. So questions may come, like problematic questions may come. Say you have been given the field dry density, some values x, say, and in maximum dry density that is obtained in the lab test as y, you might be asked to find out what will be the relative compaction. So I hope this chapter is quite clear to you. If you have any problems or queries, do comment in the below section. I'll try to solve your problems in my next videos. Do like, comment and subscribe my videos for more updates. Thank you.